And we have made it to the end of the end. The final review video for this final exam. Now this one's all about optics, or the study of light. Light is an electromagnetic wave, which means it is a mutually propagating electric field and magnetic field. It does not need a medium to travel through. Now visible light is just part of a wider electromagnetic spectrum. In fact, visible light is the tiniest little sliver of it. It includes stuff like radio waves, and microwaves, and infrared, and visible light, and ultraviolet, and X-rays, and gamma rays, all that kind of good stuff. It all fits into one spectrum. It's all the same thing, just differing wavelengths and frequencies. Now, different materials have different indices of refraction. Now, the index of refraction, all it is a difference in how fast the electromagnetic wave travels through it. So, in a vacuum, or pretty much air, light travels at 3 × 10⁸ meters per second. And this is, as far as we know, according to general relativity, special relativity, the cosmic speed limit. Nothing can ever go faster than this. When it goes through different materials, light might actually travel a bit more slowly. The index of refraction is simply the ratio between the speed of light in a vacuum and the speed of light in that material. The index of refraction can also be used to figure out how much light is going to bend as it passes from one material to another. This is called Snell's law. It's just n1 sine theta 1 equals n2 sine theta 2, where n1 is the index of refraction of the first material, theta 1 is the angle of incidence. Now, theta 1 is not the angle from the surface to the light ray. Oh, no, no, no. Theta 1 is the angle from the perpendicular, an imaginary perpendicular line to the surface, to the light ray. Same deal with theta 2. Once it's passed into the second material, theta 2 is just the angle from the perpendicular to the surface inside the material to the light ray once it passes through. The higher index of refraction, the lower the angle will be for you, and the lower the index of refraction, the higher the angle, according to Snell's law. You'll need to know about total internal reflection as well. This is a special case of Snell's law, where you start from a higher index and are heading toward a lower index. Ordinarily, it would just refract out like normal, but if you pull theta 1 up enough, eventually you'll get theta 2 to be exactly 90 degrees, meaning that light ray is just skimming the surface and not actually leaving. Any angle higher than this, there won't be any refraction because Snell's law breaks down, and you end up with just reflection back into it. Total internal reflection. You need to know about lenses too. The thin lens equation is simply 1 over the object's distance, and notice this is the distance from the lens. All of this is relative to the lens. 1 over the object's distance plus 1 over the image distance, again, how far the image is from the lens, equals 1 over the focal length. As lenses are crafted, they've got different focal lengths, and generally that'll be given to you. You'll also need to know the ray diagram for a thin converging lens, particularly just these 3 principal rays. You've got what's called the principal axis. It passes right through the center of the lens, perpendicular to its surface. Meanwhile, you've got an object, let's say its base is right on the principal axis, and it has a certain height. From the tip of that arrow, up at the very top, you will have one ray that comes off the arrow, hits the lens, and refracts, and passes through the focal point. So F is the focal distance, the focus, away from the lens. This I'll go ahead and call SO, that's the distance of the object, and SI is the distance of the image. All right, so the first ray comes off parallel to the principal axis, strikes, goes through the focal point, and down. The second ray does the exact opposite. It starts by going through the focal point on the other side first, hitting the lens, and coming out parallel to the principal axis. So parallel to focus, focus to parallel, and finally you've got the last ray that comes down, and it strikes the lens at the middle and just continues on through. Where those 3 lines intersect, you get your image. If your image is upside down, it is said to have a negative height. Speaking of heights, you can find it using the thin lens magnification. If HO is the height of the object, which will simply be the length of the object from the principal axis up to its highest point, that'll be HO, and HI will be the height of the image, then the magnification, which is just a unitless quantity, will be HI over HO, also known as negative SI over SO, meaning negative image distance over object distance. So, for the example of a thin converging lens, which is really all that we had time to get to, it produced an upside-down inverted image. So HI is negative, the magnification is also negative. The magnification can be bigger than 1 if the image is taller. It can be smaller than 1 if the image is shorter. And coming up toward the end, you need to know a bit about polarization. For light, polarization is just the direction that the electric field is propagating, not the magnetic field. If unpolarized light arrives at a polarizer, by unpolarized light, I mean the incoming light rays have an electric field going in random directions. So if you've got a polarizer with, let's say, a vertical transmission axis, it will let in half of the incoming light. It's because all the incoming light has X and Y components. It'll block out all the X components, let in all the Y components, so in total, half will get through. However, if already polarized light arrives at a polarizer, the amount that gets through depends on the angle between the polarization of the incoming light and the transmission axis of the polarizer. Use these two equations to solve for how much light, compared to what there was before, actually has gotten through. And the last slide of the last PowerPoint of the year. This is about the double slit experiment. If you send a light beam through 2 small slits, you get an interference pattern. That's because each slit becomes the source of a ripple wave. As light ripples outward, it interferes with the ripple from the other slit. In some spots, that interference will be constructive. In other spots, that interference will be destructive. So you'll get bands of light and bands of dark. Now, if you define y as the distance between the center, where there's always a bright spot, and a different bright spot, and L is the distance between the slits on the screen, then you can solve for an important angle theta simply by using right triangle trig and the tangent. Then if you know the distance between the 2 slits, you can solve for the wavelength of the light that's going through. Using some fancy geometry, which I won't hold you responsible for, you really just need to know the end result. D times the sine of theta equals m lambda, where m is called the order. If you go from the center bright spot to the next one, m is just 1. If you go from the center bright spot to 2 bright spots over, then m is 2, and so on and so forth. And that about wraps it up. Congratulations on making it this far. I know it may be stressful now. It is almost done. Take your time. Put together any questions you may have. The week of the exam is all about questions from you. So let me know what you need, and we will get it done. Thanks for an awesome year. You people are the best. See you later.